Hello everyone, and welcome to the series on intermediate statistics, and today we're going to be talking about a topic known as estimation theory, and we will talk about what it means for an estimator to be unbiased. You may have even heard this this type of statistic or this type of estimator mentioned in your elementary statistics course, but today I just want to make sure there are a couple of theoretical foundations that are mastered so that you truly know what it means for an estimator to be unbiased. So we have a statistic, theta hat, and we're going to call it an unbiased estimator for some parameter theta, if and only if the expected value of that random variable theta hat is equal to theta. Now keep in mind what we're aiming to do here. We're trying to make inferences about a population where the population has these parameters theta using these values theta hat, which are based upon random samples that are coming from these subsets of this population P. And since we're gathering random samples, the calculations on those random samples are random variables, theta hat. So since that is a random variable, that random variable has a probability mass or probability density function, whether it be a discrete or continuous random variable. And since it has a distribution, it also has an expected value. And some people may also call it the mean of the random variable. So let's actually work through a basic theorem that you probably even worked through in your elementary statistics course. And let's state it as follows. So let's suppose that x is a binomial random variable with parameters np, and let's suppose we define p hat to be equal to capital X divided by little n. Sometimes little n is referred to as the sample size of the sample. Then p hat is an unbiased estimator of P. If you want to just quickly take a few minutes to see if you can prove this on your own, feel free to do so. But the proof is actually very straightforward. So how to prove this? So what we're going to do is we're going to take the expectation of this random variable P hat, which by definition of P hat is going to be the expectation of capital X over M. Keep in mind n is just a constant, so 1 over n can factor out of the expectation operator. That's going to be true whether x be discrete or continuous, because expectations are technically just sums and integrals in disguise. So we're just going to have the expectation of x. Since x is a binomial random variable, the expectation of x is just going to be equal to n times p. You probably have already proven that. And then 1 over n times np, that's just going to be equal to p. Therefore, we have the expectation of p hat is equal to p. Therefore, p hat is an unbiased estimator of p. All right, so that's actually quite an easy proof. In the realm of unbiased estimators, we sometimes will define the bias of an estimator theta hat for parameter theta to be equal to the difference, so this is a definition, the difference between the expectation of theta hat and the parameter. So obviously, if theta hat is an unbiased estimator for theta, then the bias of theta hat for theta will be equal to theta minus theta, which is equal to 0. All right, so let's actually work through a little bit more of a involved example. Let's suppose x is a continuous random variable whose probability density function is given to be e to the minus x minus delta for x in the, let's say the interval delta to infinity, and let's assume it's 0 for x belonging to minus infinity to delta open. I leave it for you to verify that this is a probability density function for x. That is, it satisfies the non-negativity condition, and the integral from minus infinity to infinity of this density function must be equal to 1. And if you know the exponential distribution, you might even notice that this is actually just a shifted version of the exponential lambda equals 1 distribution. Right? So if this is our probability density, what is the expected value of x? Right, so x is a random variable with this probability density. So what is its expected value? So we already know by definition this is going to be equal to the integral from minus infinity to infinity of x times f of x dx. So since it's supported on delta to infinity, this is just simply the integral from delta to infinity of x times e to the minus x minus delta dx. A quick u substitution, let u be equal to x minus delta. Equivalently, x is going to be equal to u plus delta, forcing du to be equal to dx. And obviously, if x is belonging to delta to infinity, u will belong to the interval 0 to infinity. So we can rewrite this integral as the integral from 0 to infinity of u plus delta times e to the minus u du. From here, we can distribute our exponential over, and then we can distribute our integral over, and then we're going to have the integral from 0 to infinity of u e to the minus u du, which should be an integral that you're familiar with, and then plus delta times the integral from 0 to infinity of e to the minus u du, which is an integral that you definitely should know by now. So I leave it for you to verify these basic calculus integrals, that this is going to be 1 plus delta times 1, which is equal to 1 plus delta. So that's the expected value of this continuous random variable that we have defined already. So what are we going to do with this expected value? So we have this parameter delta. Now, what is delta? Maybe you do or do not know what delta represents here, but maybe we want to estimate this parameter delta with a sample. So what we want to do is as follows. So let's suppose that x1, x2, down to xm is a sequence of independent and identically distributed random variables with probability density given to be f of x is equal to e to the minus x minus delta, x greater than or equal to delta, 0 otherwise. Right? So if we take a bunch of values or samples from this population distribution, look at their values, add them up, and divide by how many we collected. So we're going to find x bar to be equal to 1 over m, x1 plus x2 all the way down to xm is, and this is the big question, is x bar an unbiased estimator for this parameter delta, for which we do not know, maybe, or most likely. Take a moment and pause this video if you want to sort of try this on your own. What we can do is find the expectation of x bar, and keep in mind the expectation of x bar is just going to be equal to 1 over n times the expectation of xm added, right? So the expectation of x bar is 1 over n times the sum from k is equal to 1 to n of the expectation of xk. And keep in mind that's true even if these variables were not independent. So each of these expectations is equal to 1 plus delta, so this is actually just going to come out to 1 plus delta all over m. So if this is truly unbiased, then the bias of x bar for delta should be equal to 0. But this is 1 plus delta all over m minus delta. And obviously this is not equal to 0 for all m, right? So therefore, x bar is what we call a biased estimator for delta. And even if n goes to infinity, then this is going to vanish, and we're still not left with delta, unless delta is equal to 0. Right? So even if n is super, super large, this still does not eliminate the bias of this estimator. It doesn't mean this estimator is completely useless, though. So one can ask, can we manipulate x bar to be unbiased? That is, can we take its bias and remove it by using just algebraic manipulations on x bar? And it's very important to note, make sure it doesn't have delta in it, because we're trying to estimate delta, so we can't have parameters that we usually do not know in an estimator of that parameter. So what I want to do, or maybe you even want to pause this video and see if you can manipulate this definition of x bar so that it is equal to lambda, such that it actually does come out to be something that is unbiased for delta. So what I'm going to do is I'm going to define delta hat to be equal to the sum from k is equal to 1 to m of xk. So you take your sample values, you add them all up, and once you do that, subtract by 1. My claim is that delta hat is an unbiased estimator for delta. So take all your observations and subtract by 1 after you add them, and it does have no bias associated to it. So let's do a quick proof. Maybe you even want to try this on your own. So let's see what we get. So the expectation of delta hat will be equal to the sum from k is equal to 1 to m of the expectation of xk minus the expectation of 1. Keep in mind 1 is not a random variable, so the expected value of 1 is just equal to 1. And then we're going to have the sum from k is equal to 1 to n. So each of these xk's are identically distributed and independent. And since they're identically distributed, they all have the same exact expected value. 1 plus delta divided by m minus 1. Notice that this is just a number that's independent of k, so we're just adding up that number n times. So it's like 1 plus 1 plus 1 plus 1 plus 1 n times, which is just going to be equal to n times that number. So this is going to be equal to n times 1 plus delta all over m minus 1. N's cancel here, so we're just going to left with 1 plus delta minus 1, which is equal to delta. So since the expectation of delta hat is equal to delta, this of course forces that the bias between delta hat and delta is equal to 0. And since the bias of delta hat for delta is equal to 0, that means delta hat is an unbiased estimator for delta. So this kind of proves that if you have an estimator that's not quite unbiased, you can always you can sometimes, most of the time actually, manipulate it algebraically so that it actually does turn out to be unbiased, which is a good property to have. One of the early statistics that we learn in elementary statistics is the sample variance. And a common question that we usually get when we're learning statistics is, why do we divide the sample variance by n minus 1 instead of n, since the formula for sigma squared is the sum of xk minus mu squared over capital N, not capital M minus 1. And the reason is if you divide by little m for the estimator, you will actually not get an unbiased estimator for sigma squared. But if you divide by little m minus 1, the claim here is that you get an unbiased estimator for it. That is, the bias between s squared and sigma squared is equal to 0. See if you can take a moment, pause this video, and prove it on your own. Else, let's get right into it. So obviously, if you do not know how to prove the unbiased estimator, then obviously we usually start off with the definition. So we need to take the expectation of this random variable, s squared. Keep in mind, 1 over n minus 1 is just a constant, so we can factor that out completely without any issues. So we're going to have 1 over n minus 1 times the expectation of the sum from k is equal to 1 to m of xk minus x bar, the quantity squared. I want to expand that form out just to see if we can do anything there. So we're going to have 1 over m minus 1 times the expectation of the sum from k is equal to m, and then we're going to have xk, the quantity squared, minus 2 xk x bar plus x bar, the quantity squared. Now keep in mind, with respect to summations, x bar is a constant. So I highly recommend working out the summations first and then doing the expectation rather than the other way around. So we're going to have 1 over n minus 1 times the expectation. And then what are we going to have? So we're going to have the sum from k is equal to 1 to n of xk squared minus 2x bar times the sum from k is equal to 1 to n of xk, and then plus x bar, the quantity squared, times the sum from k is equal to 1 to n of 1. And then we work out this to the best of our ability. Recall that the variance of x is equal to the second moment minus the mean squared. So we can take advantage of that in this particular statement. Do you see where we can use it? Maybe. We'll see. So what we have here is what? Let's take a moment. So note that here, this is the sum of the x, which is the same as what? So keep in mind the average is 1 over n times the sum of x. So if I multiply both sides of this equation by x, we have that the sum of x is equal to n times x bar. And here, that's just going to be equal to n. So we're going to have 1 over n minus 1 times the expectation of the sum from the k is equal to 1 to m of xk squared. Right? That's where our second moment's going to come into the picture. And then we're going to have 2x bar times, and that's going to be equal to n times x bar. And then we're going to have x bar squared times m. Notice here we have n x bar squared, n x bar squared in disguise, and we have minus 2 of them. So minus 2 plus 1 is going to be equal to minus 1. All right, so we're going to have 1 over n minus 1 times the expectation of the sum from k is equal to 1 to n of xk squared minus 2x bar squared. Not minus 2, but minus 1. Right. So now I'm going to distribute my expectation, and that's going to give us what? So we're going to have 1 over n minus 1. Expectation can distribute inside of the summations, so we're going to write it as the sum. That's an ugly summation. So we're going to have the sum from k is equal to 1 to m of the expectation of xk squared, and then we're going to have the expectation of x bar squared. So the expectation of x bar squared. Right? Keep in mind, xk is a random variable. That means x bar is a random variable too. So the expectation of x bar squared is not x bar squared times the expectation of 1. Now I'm going to use that little thing I mentioned. The variance is equal to second moment minus mean squared. And keep in mind, that means that the second moment will be equal to the variance plus the mean squared. Right? It's almost like sigma squared plus mu squared, which is pretty much like Pythagorean theorem in disguise. So what is the expected value of xk squared? So that's going to be equal to the second moment. So that's going to be equal to sigma x squared plus mu x squared. And that's inside the sum. And then what is the expectation of x bar squared? Well, that's going to be sigma x bar squared plus mu x bar squared. Now you may remember from elementary statistics that mu x bar equals mu x, and sigma x bar equals sigma x all over the square root of n. If you do not know these theorems, I highly recommend being able to prove them. They are very, very important. Nonetheless, notice that that doesn't depend on k, so that's just added to itself n times. So we're going to have 1 over n minus 1 times n times sigma x squared plus mu x squared. And then over here we're going to have sigma x squared all over n plus mu x squared. From here we can distribute our n, distribute our subtraction, and let's see what we get in the end. I think we also missed a n sign. Yeah, we have minus 2n. So let's throw n there before we forget about it. And let's distribute that n because that fraction is definitely going to make things not so nice if we forgot about it. So then we're going to have n sigma x squared plus n mu x squared minus sigma x squared minus n mu x squared. N mu x squared minus mu x squared will cancel, and then we're going to left with two scalar multiples of sigma x squared. So 1 over n minus 1 times, so if I factor sigma x squared out, we're going to have n minus 1. And look at that, the n minus 1s will cancel, just leaving us with sigma x squared. So therefore the expectation of s squared is equal to sigma x squared, implying that the bias between s squared and sigma s squared is equal to 0. Completing the proof that the sample variance, when you divide by n minus 1, is an unbiased estimator for the population variance. So here's a question for you. Are unbiased estimators unique? Well, think about it. If you have a population, let's call it P, of population size n, and you want to estimate it with something, what you can do is you can grab a sample, S, calculate x bar, and one can show very nicely that the expected value of x bar will be equal to mu, the population mean. But is x bar the only unbiased estimator of P for mu? The answer is no, right? So maybe x bar has some other properties, which we'll talk about in the future, that maybe other unbiased estimators do not have. And that could either be good or bad. One famous, another unbiased estimator is what we call the stratified weighted average of sample averages. So what we're going to do is suppose that x bar 1 is the average of sample with little n1 values, and let's define x bar 2 the average of Sn2, where n1 plus n2 is equal to little m, which obviously is less than or equal to capital N, with Sn1 intersection Sn2 mt. So what we're doing is we're going to be taking a sample. First, we're going to be taking our population and partitioning it into two populations, P1 and P2. We're going to take a sample from P1. We're going to call it S1. We're going to take another sample, call it S2. We're going to calculate an average for that, an average for that, and then we're going to calculate the weighted average of those two means. So what we're going to do is we're going to define, let's call it mu hat, to be equal to n1 x bar 1 plus n2 x bar 2 all over n1 plus n2. Take a moment and see, is mu hat also an unbiased estimator for mu? Take a moment and see if you can verify that. So, how are we going to prove it? Well, if you don't know how to prove, always start with the definition. So the expectation of mu hat is going to be equal to the expectation of this newly defined object. n1 just a number, x bar 1 a random variable, n2 just a number, x bar 2 a random variable, and then m1 plus n2 just a number. So this is going to be equal to what? So since 1 over n1 plus n2 is just a number, we can factor that out. So we're just going to be left with 1 over n1 plus n2 times the expectation of this object. So this is going to be equal to the expectation of n1 times x bar 1, which is x1 plus x2, all the way down to xn1 all over n1, and then plus n2 times x1, a new one, x2, all the way down to xn2 all over n2. And to avoid complications, this is from sample 1, and this is from sample 2, right? So x11 and x12 are not and cannot be equal to each other. Well, they can be equal to each other in value, but they're not the same individual because they're coming from isolated samples with no overlap. So notice that these n1s will cancel, these n2s will cancel, And then we're going to be left with what? So we're going to have 1 over n1 plus n2 times the expectation of the sum from k is equal to 1 to n1 of x1k. And then we're going to have the sum from k is equal to 1 to n2 of x2k. And then we can distribute our expectation over the sum of the sums, and then within each of those sums. And then we're going to have 1 over n1 plus n2. And then we're going to have the expectation of, well, no expectation. Let's look at the value. So we're going to have the sum from k equals 1 to n1 of the expectation of x1 k, and then plus the sum from k is equal to 1 to n2 of the expectation of x2k. Keep in mind, even though x1 and x2 come from different samples, both samples come from the same population. So this is going to be equal to 1 over n1 plus n2 times the sum from k is equal to 1 to n1 of mu x, the mean of the entire population for which sample 1 comes from, and then the sum from k is equal to 1 to n2 of mu x, the population mean for which sample 2 comes from, which is the same as the population that the sample mean of sample 1 comes from. So it's just the same number added to itself n1 times and n2 times respectively. So we're going to have n1 plus n2 times n1 times mu x plus n2 times mu x, and we can clearly see that mu x will factor out of that, leaving us with n1 plus n2, canceling with the n1 plus n2 on the bottom, proving that the expectation of mu hat is equal to mu x, forcing the bias to be equal to 0. So what does that mean in terms of stratified sampling? So stratified sampling, and in case you don't remember what stratified sampling is, you take your population, you partition it into a bunch of smaller populations, and you sample simple random samples from each of those populations, and that's what we call stratified sampling. It pretty much is a lot easier if you know people who are sampling from those smaller subdistricts. So stratified sampling preserves unbiasedness of weighted averages of sample means. So in some sense, sample means are still unbiased, and when you're working with stratified sample, you can still get an unbiased estimator by doing the weighted average of those sample means. Now, so what have we talked about today? So we've introduced the concept of unbiased estimators for population parameters. We've also discussed how you can take a biased estimator and kind of algebraically manipulate it into an unbiased one. Now, for example, if we have the binomial example that we did earlier, and we have theta hat is equal to p hat, we know that p hat and theta hat are unbiased estimators for p. But what if we add 1 over n to that particular object, right? So pretty much what we have here in disguise is capital X over n plus 1 over n. Does this turn into an unbiased estimator for p? The answer is obviously no, because if we take the expectation of theta hat, we're just going to be left with the expectation of p hat plus 1 over n. Now the expectation of p hat is p, but the expectation of a number is just itself, so we have p plus 1 over m. But one thing that's very interesting is, at least in the realm of statistics, we usually always want our sample size to be arbitrarily large. So if we take the limit as n goes to infinity of the expectation of theta hat, we're going to have the limit as n goes to infinity of p plus 1 over n, and p doesn't depend on n. P hat might, but p does not. But 1 over n converges to 0, just leaving us with p. Right? So from the perspective of bias, this can be equivalently written as the limit as n goes to infinity of the bias of theta hat and p. Theta hat and p is equal to 0, right? Because we know p is unbiasedly estimated by p hat. So what we usually call theta hat, because theta hat obviously has bias, right? So it has bias. But as n gets really, really large, the bias tends to 0. So we say that theta hat is an asymptotically unbiased. Asymptotically unbiased. It's not unbiased in the finite realm of m, but it's asymptotically unbiased. That is, it converges to an unbiased estimator of p. Because sometimes you might not be able to algebraically manipulate theta hat into something that's a direct unbiased estimator of p, but maybe, even though theta hat might not be unbiased for small values of n, maybe it has other properties that you don't want to algebraically manipulate. That is, you want to preserve other properties, but kind of keep the biased nature of it. But as long as n goes to infinity, we do tend to an unbiased estimator of that population parameter. So these are definitely some things that you definitely should know when working in estimator theory. And this property, known as the unbiasedness, is only one of a few properties for estimators that you usually want. And we'll talk about the others in upcoming videos. So I hope you enjoyed this one, and I'll see you in the next one. Take care.